Sagittarius A*, is the central supermassive black hole in the Milky Way. Its mass is 4.154 million times that of the Sun, and its diameter is 51.8 million kilometers. Despite its enormous mass, the black hole emits very little radiation. Its bolometric luminosity is approximately 100 times that of the Sun, making it difficult to detect, if not for its proximity. The discovery of Sagittarius A*, dates back to February 14, 1974, when the National Radio Astronomy Observatory and Robert Hanbury Brown first identified the black hole. The center of our galaxy has long been a mystery to astronomers. This changed in 1931, when Carl Jansky, a radio engineer working for Bell Telephone Labs, conducted experiments that laid the foundation for radio astronomy. His task was to investigate the direction of thunderstorm interference, for which he built an antenna capable of detecting radio waves with a wavelength of 14.6 meters, 20.5 megahertz. In December 1932, Jansky presented his results, in which he discovered a constant hissing noise of unknown origin. He noted that this hiss changed direction over the course of a day, leading him to propose that the source of this interference might be related to the Sun. However, in subsequent work in 1933 and 1935, he concluded that the source of this interference was located at the center of the Milky Way. Jansky suggested using parabolic antennas to obtain more accurate data, but his proposal was not supported in the United States. In 1937, radio amateur Grote Reber built the first radio telescope with a parabolic mirror about 9 meters in diameter and created a map of the radio spectrum, where the central regions of the Milky Way and the bright radio sources Cygnus A, Sig A, and Cassiopeia A, Cas A, were visible. This was an important step in studying the center of our galaxy. By 1960, Jan Oort and H. Roger had established that a radio source called Sagittarius A was located close to the galactic center. In 1966, D. Downes and A. Maxwell, analyzing radio observation data, concluded that this source was associated with a small nucleus of the galaxy, about 10 parsecs in diameter. In 1971, it was discovered that the source consists of two diffuse clouds. The eastern part, SGR-A, emits a non-thermal radio spectrum, while the western part, SGR-A*, is a cloud of hot ionized gas with a diameter of about 45 arcseconds. With the development of infrared astronomy in the 1960s, it became possible to overcome the obstacles posed by dense clouds of cosmic dust that hindered observations. In the mid-1970s, with the improved resolution of telescopes, new infrared sources were detected in the gas clouds surrounding the galactic center. Some of these were identified as young supergiant stars, while others were identified as young giants. These studies helped to more accurately determine the mass of the central object, which at that time was estimated to be 3106 solar masses. By 1985, it became clear that the central black hole was located in the IRS-16 source, and researchers discovered two powerful streams of ionized gas orbiting, which allowed for an even more accurate mass estimate of 7 to 106 solar masses and 5 to 106 solar masses depending on the flow. But the researchers did not stop there. What happened next? What recent study was conducted by scientists? And what secrets did they uncover with images that could change everything we knew about space and its laws? In 2022, scientists from the Event Horizon Telescope, EHT project, presented a historic image of the Sagittarius A*, black hole. In this image, the black hole appears as a dark cloud surrounded by a bright ring of light. However, a new analysis of the data conducted by EHT researchers shows that the accretion disk of this black hole has a different shape than previously assumed. This means that the initial image did not reflect the true structure of the supermassive object. Researchers argue that the previous data analysis contained errors and did not allow for the true shape of the accretion disk to be seen. Using a new method of analysis, scientists determined that the accretion disk of the black hole has an elongated structure rather than the ring-shaped one shown in the 2022 image. Additionally, in August of this year, EHT specialists introduced a new method for studying black holes that will allow for a clearer image of Sagittarius A asterisk in the future. This could help shed light on the precise physical structure of this mysterious object at the center of our galaxy. What are the key differences between stars of different populations, and what can they tell us about the development of the Milky Way? Can studying stars provide answers to questions about the fate of our galaxy? The stars of the Milky Way are not uniform in age and composition. They form three main populations, population 1, 2, and 3, each with its unique characteristics, which allow astronomers to trace the evolution of our galaxy. The division of stars into these populations is based on their chemical composition, age, and location in the galaxy, providing insight into how the Milky Way has developed over billions of years. Population 1 includes young stars that make up the majority of the stars in the spiral arms of the Milky Way. These stars generally have low amounts of elements other than hydrogen and helium, such as carbon and oxygen, which form in later generations of stars. An important feature of stars in this population is the presence of planetary systems. Studying these stars helps astronomers understand how planets and other celestial bodies form, as well as reveals the conditions that might support the emergence of life. Our solar system, with its planets and other celestial bodies, is a typical representative of population 1. These stars are commonly found in the central part of the galaxy and in its spiral arms, where the density of gas and dust creates optimal conditions for new star formation. Population 2 consists of older stars, which make up the majority of stars in the galactic halo, the area surrounding the spiral disk. These stars have higher amounts of heavy elements compared to stars in population 1, indicating their ancient origins. Their age can reach tens of billions of years, making them some of the oldest objects in the Milky Way. Stars in population 2 typically have lower masses, which prevents the formation of planetary systems. Although such systems can exist, they are less common. These stars are mainly found in old globular star clusters and in the galactic halo, which reflects the early stages of the galaxy's formation. An example of a population 2 star is the binary star Gamma Cephei, located 45 light-years from the Sun. Population 3, although hypothetical, represents the first wave of stars formed right after the Big Bang, when the universe had no heavy elements. Since these stars were very large and hot, they did not last long. None have survived to this day, but the James Webb Space Telescope is capable of detecting the light left behind by them. Analyzing data from the JADES project, scientists found evidence of population 3 stars in the galaxy GNZ11, one of the farthest galaxies from Earth visible with telescopes. At a certain redshift value, the Webb telescope sees the galaxy as it appeared about 13.4 billion years ago, 400 million years after the Big Bang. The heat of the first stars was thought by scientists to have ionized all the helium around them, prompting them to search for unexpected signatures of this helium, which were indeed discovered. However, this was only the first step in studying population 3 stars. These stars are not the only objects capable of ionizing helium. Astronomers continued their research and identified a range of characteristics that led to a new discovery. During their analysis, they encountered a spectral feature that could be considered strong evidence of photoionization by population 3 stars. Furthermore, the volume of ionization indicated a specific mass for these stars which matched model calculations, confirmation of the existence of population 3 stars in the galaxy. GNZ11 will only be possible through subsequent astronomical observations, which will help definitively establish this fact. Each of these populations represents a crucial element in understanding the structure and evolution of the Milky Way. How does dark matter influence the rotation of stars and the overall structure of the Milky Way?